I wrote here, lesson 3, friction. Friction, if you zoom in on an object, even though it may seem smooth, when you zoom in microscopically, you'll see that there are little hills and valleys on that surface, and friction is due to the interlocking of those molecular hills and valleys between a surface and an object on the surface. Although the surfaces may appear smooth, on the atomic scale, when you zoom in, Mickey, they are not. Friction resists sliding, and as such, it can resist motion when you're trying to slide an object across the floor. Or, I've tried to convince you, it can also create motion, because it's the force that pushes you forward when you walk. It's the force that's pushing you forward when you bike. Example 1. Draw the force of friction in each case. If you have a sliding block and the block is moving to the right, which way is the friction force going to be? Which way is the friction force going to be? More specific in this case, please. To the left. A car speeding up. This one's a bit trickier. What you have to do is use your imagination to follow the tires all the way around. It seems to me that when I follow the tires all the way around, the tires are pushing backwards. Relative to the road, they're moving backwards. Friction resists motion, so which way will friction push? And this is one that kids have a lot of trouble with. Not just kids, teachers. There was a physics teacher that I was working with in one of the other high schools who was teaching this wrong, who was saying that the engine pushes the car forward and friction slows the car down. No. Friction is what, the engine has nothing to do with it. The engine is what applies a rotational force to the tires, but the tires are what's in contact with the road. The tires push back against the road, friction pushes the car forward until you hit the brakes. If a car is slowing down, now what you're trying to do is you're trying to get the tires to rotate in that direction relative to the road. You're trying to get them to push forwards against the road. Which way will friction act then? Backwards. What happens when you demand more of friction than it can give? You skid. Newton's first kicks in. Okay. You skid. The amount of friction depends on two things. The first thing that it depends on is the types of surfaces that are in contact with each other. Ice, not much friction. Teflon, not much friction. Sandpaper, more friction. Glue, way more friction. And in fact, Petra, we have a number that describes how sticky one object is in comparison to something else. We call it the coefficient of friction. Now, a lot of students think that that's a force. It's not. All it is a ratio. What's its symbol? A Greek letter. What Greek letter? Right? Greek letter mu. We use that symbol, Kelly, for the coefficient of friction. Okay? What are the units for this? Nothing. It's not measured in newtons. It's not measured in meters per second squared. It's unitless. In fact, I'll prove it to you a bit later on. But the bigger this number, the stickier the objects are. Ice has a coefficient of friction of about 0.01, especially when steel on ice. That's why ice skaters can glide for so far. Rubber on tires on pavement, rubber on concrete, about 0.75. That's why we use rubber in tires. Can you be bigger than 1 Yeah. Usually, I'm going to give it to you, it'll be a decimal between 0 and 1. Bigger than 1 means you can support your own weight and some more weight. Glue, bigger than 1. Although, not just glue, dragster tires, professional dragster tires, those have coefficients of frictions of around 3 or 4. Not 0.3, but around 3 or 4. Why would dragsters want sticky tires? What force is pushing? Yeah, friction. You want as much friction as you can. And again, to a non-physicist, they'll say, wouldn't the sticky tires like stick to the pavement and slow them down? No. Friction isn't what's slowing a car down. Friction is what's pushing a car forwards. You want as much as you can. In fact, if you've ever gone to a drag race, the reason they always do a little smoke show, they're melting the tires slightly before they start. What would melting it do? What have you noticed about melted rubber compared to normal rubber? Stickier or less sticky? Much stickier yet. The smoke show isn't for the fans, although the fans like it. It's if we get the tires melty and hot, even better. There's physics behind it. So it depends on this coefficient of friction, symbol mu, which is a dimensionless quality. If mu is large, lots of friction. If it's small, not much. And it depends on one more thing. The force pushing the surfaces together, which for a lot of people would just be gravity. But it's much more complicated than that. Pause the video. Went on a little rant here, okay? Consider the block below, which is being pushed by student number 1 across a rough surface. You know what? When they say the phrase rough surface, I think what they mean here is include friction. If they say smooth surface or slick surface, I think what they're saying, Alex, is ignore friction, right? And it's being pulled by student number 1 at, that's an important phrase. What does constant speed tell me? And if my acceleration is 0, what does that tell me? In terms of this unit, in terms of forces, what does that tell me? They're in equilibrium. The net force is 0. Everything's balanced, whichever way you want to think about it. Suddenly, you know what? Let's personify this. Hakeem is pulling one of the gym benches across the gym floor at a constant speed. Suddenly, Elijah decides to jump on the bench, because that never happens when you guys are trying to move those things ever. So Elijah decides to jump on the bench with a force F. If Hakeem continues to maintain a constant applied force, what happens to the weight, the normal force, friction, and the motion of the block? Explain your answer. There's a picture. Okay. What happens to the weight? What is weight? What happens? So W equals mg. Does the mass of the bench change? Does G change? So what happens to the weight? What happens to the normal force? Well, let's look at my free body diagram here. So in my free body diagram, I would still have mg. But now I have force F. How about we'll call it Fe for Elijah. Oh, sorry, I already got extra push F on there. I'm sorry, guys. I typed it in. That was dumb of me. Right there. That's why I always put the arrows in the middle. I like to put the tail in the middle. I don't notice arrows coming in. That's okay. What happens to the normal force? Why? In fact, I can tell you exactly how big the normal force has to be. It has to be this big plus what? that big. The normal force is going to have to be increases. And make that a subscript. Yeah? Okay, what else did they want me to talk about? What was the next thing they wanted me to mention or comment on? What happens to friction? Bigger, smaller, or stays the same? Why? And this is why we defined friction last year. Again, if you want to annoy me this year, I dare you when I say, how do I calculate friction? I dare you to say, oh, it's mu mg. We never defined it that way last year. We defined it as mu times the normal force. And so if the normal force increases, friction increases. What happens to the motion of the object then? Elijah, why? Now, got to get tech. He's right. It's going to stop. Will friction get bigger than the applied force? Convince me. You know is correct. Why? If it got bigger, what would happen to the bench? Would suddenly rebound going backwards. This is why, Bree, I said, I think it was you, I said this earlier too, friction is only as big as it needs to be. Friction could get bigger if it needed to when you sat on the bench, but I'm telling you, how big is friction going to get? Big enough to stop and shut Hakeem down, and no second of a Newton bigger. No tiny bit of a Newton bigger. Oh, and if Hakeem pulls harder and it doesn't move, friction just got bigger to match Hakeem. It's as big as it needs to be. And if Hakeem, lifting weights, and gets it moving again, now you just applied a force bigger than friction could ever be. That's what's going on there. So friction increases to match pulling force. To match student one's force. So to explain your answer using principles of physics, I think we kind of just did in this argument, and we kind of have verbally. I could do a good free body diagram and walk it through. It is good. And that is why we say this. Friction is mu times the normal force. Does anybody notice anything strange with my notation in this question? Elijah, what? Why did I leave the vector off the normal force? It is not in the same direction as friction, as a matter of fact. The normal force points up, friction points perpendicular to the normal force. Or, if the normal force is pointing, well, turn the page. A student gives an old shopping cart a big push, on a flat, rough surface. What do I mean by rough surface? Include friction. Which of the following is the best force diagram for the cart after the student has released it? Once again, we're going to do our traditional voting. Once again, it's how high you hold your hand up. Now what we're talking about, look here please, is this. Imagine my chair is the shopping cart. We're not talking about while I push it. We're talking about right there. Say 1 second after I push it. What's the best free body diagram? Who says A? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Who says B? 1, 2. Who says C? Was that a vote? No, she was just doing her hair. Okay. Who says D? So I got 18 people in this class. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I got 18 students and 6 cowards. That's what I have in this class. Why is A correct? Convince me. What are the forces acting on the cart? Get the obvious one. Really? What are the forces acting on the cart? Get the obvious one. Is the cart sinking into the ground? Is it lifting into the air like Superman? So vertically, the forces must be balanced. There better be an arrow pointing up and pointing down, and they better be pretty close to the same length. Which way is the cart accelerating? Is the cart speeding up, slowing down, or continuing at a constant speed? Which of those is the only diagram possible for which it could be slowing down? Cliff? A. Why can't B? What would B be? So either stopped or at a constant speed, right? Could be just going at a constant speed. What about C? Stopped or at a constant speed. In fact, B and C are the same net result, even though you've got two forces canceling themselves out in part B. What about D? That's speeding up. If to the right is speeding up. A. Why? Only FBD that has net acceleration slowing down. And what force is that? I think that's friction. That really bugs kids because when the cart moves forward, everybody wants to believe there's a force acting on it, pushing it forwards. If it's slowing down, I'm telling there is a force acting on it, but it's acting in the opposite direction. Example 5 says, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. I'll be honest, if I give this to you on a test, all I'm going to say is, hey, find the acceleration, please. I'm not going to walk you through A, B, and C. I'm going to expect that you know to do A, B, and C. Are there two separate diagrams here, Peter? Let's draw a little line down the middle of the page. Okay. What are we going to do first? It's a force question. What are we going to do first? I'm going to draw a free body diagram. Although, you know what? Now what I'm going to start to do, if they give me a lovely diagram, I'm going to label the forces on my diagram. And I guess I can't technically call that a, quote, free body diagram, because in a free body diagram, Claire, you're supposed to represent the mass as a dot. But since they gave me this lovely picture, I'll label the forces on this picture. I'll say, see that 10 kilogram? What are the forces acting on it? Get the obvious ones. Definitely going to have mg down. And this, using the diagram they gave you, is perfectly acceptable. However, if I ever ask you for a free body diagram, make sure you draw me, represent the mass as a dot, a proper free body diagram. Hey, what other forces are acting on this? Is this mass sinking into the ground like quicksand? Is it flying into the air like Superman? There's a force pointing up then. What do we call that one? Because it's normally there. By the way, the real reason it's called normal force, the word normal in math means 90-degree angle width. And that's why on that glass door example, when the normal force was coming out towards you, I could still call it a normal force because it was still forming a 90-degree angle with the surface. That's why we use the word normal. Any others? And then we have this applied force. I'll label it just so I don't forget that it's there, because I find, Sam, if I don't write something, I forget that it was in the diagram. Your brain might work better than me, and God bless you if they do. My brain works weird. Vertically, who's winning? It's a tie. So A does say write a vertical force equation. I could go like this. Winner minus loser equals 0. I could say that because there is no acceleration. Or if you really, 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 really wanted to be clever, look up. You could, if you wanted to, plus the mg over to this side, in which case you'd get normal force equals mg. Ha! That's probably what I would jump to. Either one's fine. Race, what's B asking me to find? Friction is what times what? Thank you for saying mu times the normal force and not saying mu mg, so I don't have to throw this mu at you. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. What? mg. Yes, this whole unit again. Again, to try and drum that in. That's on purpose. Hakeem's laughing. So you're saying I can go, you know what, before I put in numbers, I'm going to write mu mg in my notes. If in your homework you start going straight to numbers, I won't freak out, but I want to make sure I note what we did. So if I hear you, Race, it's going to be 0.12. Race, did they give me the mass? What? What's g? Yeah, isn't it negative? Oh, no, we said in this unit, we'll take care of the direction ourselves. Don't bother inserting the negative. We'll just let it happen with our winner minus loser. It looks like friction is what? 10 times 9.8 is 98. 98 times 0.12 is going to be 9.8 plus 1.96. It's going to be 10.8, 11.76. Woohoo! 4 sig figs in my head. 11.8 newtons, because I go to 3 sig figs in my final answer. Come on, Peter, that was some pretty good arithmetic in my head there. Peter, what's C asking me to find? All right, horizontally, who's winning? Which way do you think this thing is accelerating, if it is accelerating at all? To the right, because friction's not going to do work and let it accelerate. So to the right or standing still. So who's winning? Peter? Winner. Minus. What's the loser? Peter, my friend. And that equals my net force, which is just plain old MA. There is my horizontal force equation. Peter, what does D want me to find? I see an acceleration in my equation. C. How to get the A by itself? I heard you say divide by M, yeah. So if I hear you correctly, and I think I do, A equals applied minus friction divided by mass. I'm not going to memorize that equation. I can derive it in 2 seconds. And it's different for every single situation anyways. Peter, what was the applied? 20? Was it 20? Minus 11.76. Was it 11.76? Yeah. Divided by 10. I think I can do this in my head too. 20 take away 11 is going to be 9. Take away 0.7 is going to be 8.3. Take away 0.6 is going to be 8.24 divided by 10. 0.824? Let's make that 8 look like an 8. What if we got a negative answer? What would that be telling us? Okay, because friction doesn't actually do anything, all it would tell us is it's not moving. It's not going anywhere. Friction can be bigger than 20. It's not saying friction actually is bigger than 20. You're saying friction can theoretically be big enough to even have a bit of extra acceleration. If you got a negative answer, you got your winner wrong. Start over, and it's going to be friction minus applied. Next one. What are the forces acting on? You know what? The fact that there's an arrow pointing down, I don't like that. So I am going to go over here and represent the forces with a dot. What are the forces acting on this? Get the obvious one. Gravity. Are there any other forces pointing downwards in the same direction? What? I'm going to go put it right here, and I'll call it 15. Is this block sinking into the ground like quicksand? Is it flying into the air like Superman? Then there must be a force. Why did I draw the normal force so much bigger than gravity? It's got to take care of that 15. Yes? Then I have 20, which is the applied force. Here, Dueck, let's be a little clearer. Let's go 20 equals F applied. Is that it? No, you say? All right. Part A said, write a vertical force equation. Can you see it? What equals what? Oh, you know what? I forgot to put an Fn on here, didn't I? Let's do that and label my force. Now let's try that again. What equals what? Bree, was that a hand? No. Yeah. There's my vertical force equation. You could also go Fn minus 15 minus mg equals 0. I love the fact that you said, you know what, since they're balanced, I can probably just have everything up equal everything down. Yes. Curtis, what's B asking me to find, kiddo? Friction is what times what? Mu times the normal force, you say? Which in this case is going to be mu times mg plus 15. Right? Which is going to be 0.12 times 10 times 9.8 plus 15. All right, Dueck, if you're so good, do this one in your own. Do this one in my head. Well, 10 times 9.8 is 98 plus 15 is 108 plus 3 is going to be 113. 0.12 times 113 is going to be 11.3 plus 2.26, 13.26. I could be way off. 13.56. I forgot to carry the, forgot to carry the 2. 13.56, or to 3 sig figs, 13.6 newtons. What does C want? Alex, what does C want? Who's winning? Who's winning? Who's losing? You know what? It's exactly the same equation as the previous example. Friction has changed, but the horizontal forces haven't changed in terms of there aren't any new ones. Winner minus loser equals MA. And Peter, that means, how do I get the A by itself, kiddo? As you said before, what? So the acceleration is going to be the applied minus the friction, and divide that by the mass, where the applied was 20 minus, this time friction was 13.6, divided by 10. Oh, this I can do in my head. 20 take away 13 is 7, take away 0.6 is 6.4 divided by 10. 0.64, double check me. Oh, no, it's 13.56, Mr. Dueck. So 20 take away 13.56, I can be more accurate. That's going to be 7, 6.5, 6.44, 0.644. That was kind of cool. Turn the page, or next page over. Now, so far we've been looking at situations where you're sliding something, but there can be friction on an object even when it's at rest, since the hills and the valleys will lock up when we apply even a small force to an object. The force of friction on an object at rest is called static friction, because static means not moving. Technically, there are two types of friction. Here's our thought experiment. If we pull on a desk with a force of 2 newtons, like this, and the desk does not move, then which of the following is true? A, static friction is greater than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. Once again, you're going to vote. Once again, this time, no cowards. And how high you hold your hand up is how sure you are of the answer. So I'm tugging on this desk with exactly 2 newtons, and it ain't moving. Who says A, static friction is bigger than 2 newtons? Ooh. Who says B, static friction is exactly 2 newtons? Who says C? Who says D? Why must A be wrong? Ashley, when you give me the same volume after I say your name, doesn't help me. Louder, with authority. I gotta be fussy. Replace the word moving with the word that begins with A. Accelerating, because the constant speed moving, game's totally off. Accelerating backwards. If static friction was bigger than 2 newtons, I could tug and like a slingshot, it would go shooting that way. Static friction, again, Claire, is as big as it needs to be. If I tug with 3 newtons and it's not moving, how big is static friction? What about 3.1 newtons and it's not moving? What if at 3.2 it just starts to move like it just did? Static friction, the biggest it could be was 3.2 newtons. And I don't know if you've ever tried this, but I could feel it. As soon as it started to move, I didn't have to pull as hard, because now kinetic friction took over, and kinetic friction is smaller. Okay? It says, explain your answer using principles of physics. We just did. I would probably say why A and D and C had to be wrong. A and C require an unbalanced force, which would mean it was accelerating. It's not. D, there's friction to resist the force. Only B lets Newton's first be true. So you know what? My short answer would be the law of inertia, the law that says forces have to be balanced if you're not accelerating. And again, Ashley, resist the temptation to say moving. Because as soon as you say moving, I have to say, well, you could be going at a constant speed and all of the rules work then. Accelerating, right? So, static friction is thus a force that varies from 0 when you're not pushing at all, up to as big as it needs to be to prevent you from pushing it, up to once you go bigger than that, it'll start to slide. And you can calculate static friction as mu static times the normal force. If an object is sliding, we call it kinetic friction, and that's mu kinetic times the normal force. You know what? We're going to treat them as though they're the same thing. So, I'm going to skip example 7. I got a couple of videos and some homework to show you. First of all, homework. I think you can try number 1. I think you can try number 2. I think you can try number 3. 4 is good. 5 is good. 6 is a nice algebraic proof kind of a question. I'll give you that. I'll skip 7. Ten is good. 1, 2, 3, 4, 5, 6, 10. Do I want to do number 8 or not? Do I want to do number 8 or not? You know what? I'm going to try. Number 8's a good challenge for you.